Greetings. Thank you for attending this talk. Okay, so this morning, or at least morning, my time where I live, I'll be speaking about computational complexity classes, homotopy classes, and Nmachines. My name is James Boyd, and I am a project research assistant at Wolfram Research, as well as a research affiliate with the Wolfram Physics Project. Okay, let's begin. So the following presentation offers introductory comments on research in which I am currently involved. Such research engages with a relatively new research program on the foundations of mathematics. That program involving what's known as Univalent Foundations of mathematics, as well as Homotopy Type Theory, or HoTT, as well as Multicomputation, which is an approach to computation recently debuted by Stephen Wolfram and developed for the Wolfram Physics Project. So, Homotopy Type Theory, or HoTT, is perhaps a new concept for many of you, so I will, I would not dare attempt to provide a comprehensive introduction given the time allotted to me, but I can emphasize a couple of key points that are of particular relevance to the research that I am undertaking. So, homotopy type theory is an approach to type theory, which can be understood as an alternative to set theory, though set theory can also be performed within homotopy type theory. And in homotopy type theory, we treat types as propositions in the intuitionistic tradition of type theory, but we also treat types as spaces. And I'll explain what exactly the consequences of that are. So we say of some little a that it is a term of a type, in this case, big A, if little a is a program for constructing big A. And thus, according to something called the Curry-Howard correspondence in constructivist mathematics, little a is some proof of A, where we treat A as a proposition. We write this relation as such. So just to review, you have some program, you have a program for constructing some type, and because you're able to construct that type, you can also treat that program as a proof, where you treat the type as a proposition. Now, under the homotopy interpretation, we treat little a as a point in the space big A. And if big A has only one term, right, if it only has one constructor, then it is contractible to a single point and would therefore be a zero-dimensional space. However, spaces in homotopy type theory evade contractibility by merit of non-trivial homotopies. So they're not necessarily just zero-dimensional spaces. They can be more interesting than that. And it might be the case that we can construct type big A via multiple programs. So we say of two programs, say little a and little b, that they are equal if, for their identity type or their equality type, we can in turn produce a constructor or a proof, a constructor or a proof of the identity itself, okay? So under the homotopy interpretation of type theory, the term of the identity type, little a equals little b within space A, that term of the identity type is a path P, which is a one-dimensional space. And you can think of this as a one-dimensional path between the 2 points. So our original constructors are points, and if we have a proof of their identity or a program for constructing their identity, then we have a path between those 2 points, where the path is in turn a program that constructs that identity type. Now, put informally, this path P is also a program. It's a program that can simulate both programs A and B, little a and little b, and construct A with both simulations. And so we write this as follows. So you have this type, you have this term of this type, you have this term of this type, This is a program for constructing big A. This is a program for constructing BA. And this is a path between these points. It's also a program that simulates this program and shows that both of these programs construct the same type. And we're defining equality with respect to big A because that's the space. That's the type of concern here. Now, suppose that given two programs, P and Q, that serve as terms of the identity type, A equals B, little a equals little b in A. So we can in turn generate yet an additional program, beta, that serves as a term of the identity type P equals A equals B, Q. So more informally, we say of B that it simulates both Q and P, and the manner in which both P and Q in turn simulate both A and B and construct A with both simulations. So now we have this two path B, and this is a path between paths P and Q, where both P and Q are paths between points A and little b. So we're progressively moving to non-trivial homotopies based on our construction of new programs that offer higher degrees of simulatability between our other programs. So it's admissible in homotopy type theory that such higher equalities or identities be treated topologically as higher spaces. And if we construct higher identity types with terms programs, we obtain higher non-trivial homotopies. So thus, HoTT provides a structural means by which we can formalize constructability and in turn, computability. So you can take stock, you can take account of what you can construct and how you can construct it, the different ways in which you can construct it, and establish different identities between your constructors and between it can continue, so long as it's computable, it can continue to these higher non-trivial homotopies. Now, during discussions initiated at the 2021 summer school, Wolfram Summer School, and prior to my employment with Wolfram Research, it occurred to me that it might be intriguing to consider for these higher N paths, like these 2 paths, 3 paths, 4 paths, etc., N paths, these higher paths permitted in HoTT, the kinds of programs that might yield such higher paths. And I elected to refer to programs constitutive of these N paths as Nmachines. So if you have some, say, beta equals, P equals A equals B Q alpha, or, these higher maps where you're simulating quite a number of programs that are simulating a large number of other programs forming these higher homotopies, what kind of abstract machine does that? And that might sound like a peculiar question to ask, but it should be borne in mind that a number of abstract machines have emerged in the mathematical tradition, most famously with Turing, but also with Minsky and Wolfram and Conway and others. So it's a tradition in mathematics to think about machines abstractly and mathematically. And when, according to the Curry-Howard correspondence, when I see that you can have these higher degrees of simulatability, well, some kind of machine has to execute or implement that. And what exactly those machines are, I find intriguing because I think that they're rather exotic objects. And I'd like to be able to understand how we can better understand them and what kind of uses they might serve. So I pondered how one might proceed to study the computations executed by these Nmachines. After all, such machines enter what's known as univalent foundations if they construct some type, right? The types are the terms of the type are programs. So these machines are terms of some type, they're constructors of some type. Thus, its structural space, the space of this program or machine, is determined by computability. It has to be computable, has to be able to compute something, it has to be able to construct something. If it can't construct anything, then it has a very trivial place in Univalent Foundation. And so it occurred to me that the simulation of programs that yields a common result is of central importance in another field, actually. And I was actually very intrigued to consider the intersection between these two fields. And this other field is what's known as computational complexity theory, which pertains to the study of complexity classes such as P and NP for problems. So for instance, in computational complexity theory, there are certain problems that are in the class P or in the class NP, and there are problems that are what are known as NP complete. Maybe you've heard this term, NP complete. So problem is NP complete if they're solvable non-deterministically and in polynomial time via some program. The problem is solved in some way. Let's say it's solved as a Boolean satisfiability problem. Okay, but then that problem can also be simulated in another way and solved as some other problem, like say a vertex cover problem, and still solved in polynomial time. And even the term simulation is used in computational complexity theory. So this seemed like an interesting way to start looking at this, because it suggests that this NP complete class itself kind of belies or suggests that there is some sort of, it could be treated as a higher machine, the class itself. In existing theory, you have some sort of idea of being able to translate between all of these different kinds of programs. But again, what does a machine that's able to simulate all these programs and translate between them, what kind of machine exactly is that? And now, as a research affiliate with the Wolfram Physics Project, I am undertaking formal research in order to better understand the relationship between computational complexity theory and homotopy type theory. Well, I should add an additional note, which is there's computational complexity theory, which is a few decades old, but has a number of outstanding problems in it. There's univalence and homotopy type theory, which are these relatively new, I would say, basically less than 10 years. They've been pursued for less than 10 years. And this is in the area of foundations of mathematics. But as someone working at Wolfram Research and also an affiliate with the research project, I'm also very interested in how this relates to the new paradigms in computation that we are currently helping to pioneer. So this study that I've described, it strikes me as important in another respect. It strikes me as important given the recent advances made by Stephen Wolfram and others in what's known as multicomputation, which is a new paradigm of computation that permits multiple parallel evaluation of computational paths. So multicomputation arose originally during the development of the Wolfram Physics Project, but has since been identified as a novel paradigmatic approach with multiple applications. And so I'll show some examples, some kind of simple examples of multicomputation below. And as you'll see, as we generate multiple evaluation paths via multicomputation, the relevance to HoTT becomes salient, and it should provide some nice experimental means for starting to think about these end machines. So consider below. So we have a multicomputation where we're going to evaluate according to two distinct paths. And as you'll see, these paths often overlap and they form this highly non-trivial emergent structure. So we're going to send n with each iteration to n over 2 and to n over 4. And we yield this perforated, interesting structure just with these two parallel evaluations. And then if you send at each iteration n to n over 2, n over 4, and n over 8, you get a similar but somewhat less porous structure. And if you send n to n over 2, n over 4, n over 8, n over 16, you get this almost architectural looking structure. And as you can see here, there is some very interesting interplay between these multiple computational paths. They're obviously not unrelated to each other. They intertwine and intersect. There's non-trivial confluence between them. And the overall computation does not have the kind of endlessly ramified structure of a tree, which would be the case if there was, I suppose, no confluence. It actually has some sort of intriguing overall shape to it that emerges after a sufficient number of iterations. Now, well, this is somewhat of a recapitulation of what I just said, but the confluence of multiple computational paths in multicomputation, it strongly resembles, in my view, completeness, the notion of completeness in computational complexity theory, and path equality in HoTT. So remember, completeness, I mean something like NP complete, and path equality, well, this is where we had like this two path between one paths between points, but it could be n paths, and the programs that execute them would be Nmachines. And so thus, I feel as though, in addition to the mathematical work, which is kind of a combination of homotopy type theory, category theory, homology, these areas of abstract, you could call them pure mathematics, though with rather direct application to, say, questions of computability. It's also nice to be able to actually conduct what are known as computational experiments, where you're trying out, you're testing different kinds of computations and trying to understand the way in which they relate to each other. And if you see that, two computations relate to each other quite intimately, trying to understand, well, can you come up with some other higher computation that can do both of them, et cetera, et cetera. And so thus, I feel as though multicomputation offers an experimental means by which I'll complement my mathematical study of Nmachines. Now, this project is only beginning to develop, though I thought it would be instructive for me, and perhaps of interest to others, to hear some initial comments, even at this early stage. I mean, I'm excited at this early stage, and I very much enjoy talking about it, even though it's still quite embryonic. So let's see. Yes, okay. Well, thank you very much for your time. We still have about 12 minutes to do some Q&A, and so I will take a look at the page here. Well, I don't see any questions in the chat, but if you have any questions about the content that I just presented, please, there is a chat box on the page for this. Okay, so I have a question by a certain Pierre about the relation to superfunctions. And I don't know, actually, because I haven't really studied superfunctions. Now, if Pierre, if you, it depends on how difficult it would be, but if you have maybe one sentence summary of superfunctions as you understand them, as you might think that they're relevant, then I could maybe say something about it. But alas, I have not studied these kinds of functions. I was not even really aware of something called superfunctions. But well, now now obviously, no matter what, after this talk, I will look it up. So if Pierre would like to elaborate upon the question, I'd be happy to entertain it further, and also be happy to consider any other questions that participants might have. Your definition, okay, this is the question by Thomas Brenham. Your definition of P and Q appears to be self-referential, though I think in actuality, it's actually fine here, but does it make me want to ask about Gödel in HoTT? Well, whether or not, you see, I'll make a brief remark about this, which is that, you know, the fact that you can have not only multiple terms of a type, not only can you construct a type in multiple ways, and not only can you have multiple terms of identity types, such that between, say, two terms, you can have multiple paths. It's not necessarily indicative of self-referentiality, but it is indicative of something important, which I didn't have time to discuss during the talk, which is a different kind of equality known as intentional equality. You know, ultimately, you can look at Univalent Foundations and Homotopy Type Theory, at least in part, as the kind of consequence, this kind of these structural results that one obtains by beginning to consider equality in a slightly different way. And there's some good work produced on type checking and intentional versus extensional equalities by people like Hoffman. And well, basically, how should I say that? How should I put this simply? With intentional equality, you can have these multiple kinds of identity, treating identities as distinct without collapsing all of them within some, what's an extensional equality, what would just be some kind of single notion of identity. And once you allow these identities to be kind of disaggregated, all of a sudden you can start to consider their structure. Now, Gödel does have, I suppose, Gödel does come up in some aspects of homotopy type theory. For instance, people are interested in realizability. And if you look at the work of Kline on realizability, that uses Gödel numbers. But also, if you have structures that have some genus or some obstructions where you would start to work with homology, and there are obstructions to your computation, well, this might not, it doesn't necessarily pertain directly to Gödel, but I strongly suspect it does pertain to some of the ideas that Wolfram's had about computational irreducibility and the kind of inability to take some straight path in whatever computation you're doing. You have to take some circuitous or long wayward path because you have some holes or some non-trivial genus in your homotopy. Hope that helps. Okay, I have a question from Bruce. What role may ascending and descending central chains of subgroups play in your work if certain sizes are known? And what about the role of silo groups? Well, I'm not sure. I mean, what I can say about that is it does remind me of, I will say that as I began to think about this in terms of the idea of one machine able to simulate another, I did think about Krohn-Rhodes theorem, and because I have seen people speak about Krohn-Rhodes and automaton theory in this way. And this is not really the same, though, you know, their groups kind of do appear in HoTT in different ways. You can treat types as infinity groupoids, and you can think of, you can establish different identities, you can establish different paths, and then you can take predicates over those paths by performing a groupoid action. But also, as we're beginning to understand the properties of computation in my own work, this will definitely involve trying to compute and calculate fundamental groups and homotopy groups for certain kinds of complexity classes and So groups certainly do come up, but I'm not going to speak to it in any greater detail. I have a question from Andy, which is, I have heard of relations of HoTT to quantum computing. Well, I don't doubt that you've heard that, but I don't have anything to say about it. Maybe at some point, I know there is a kind of a literature on computational complexity and quantum computing, and also people are interested in compositionality and categorical approaches to quantum computing. And I imagine that there is some relevance, but so far, especially thinking about complexity classes, they've been terribly non-quantum in nature. And if it becomes relevant, then maybe I'll consider quantum computing as well. I have a question from Wolfram Insider Ian Ford. Do you have any ideas on how types fit into multi-way systems? Well, there are preprints, maybe even prints at this point now, by people like Xerxes and Jonathan and other people in the Wolfram Physics project who have been thinking about the Wolfram physics models and homotopy type theory. This is not something that I'm pioneering. I'm interested in a particular aspect of it, but it's a kind of legacy that was built, I think, with Xerxes' summer school project from last year. And then I think Jonathan began to write on it, and then a number of papers were done on it. And so I'm certainly standing on their shoulders in that regard, though my interest is on a particular aspect of it. And Xerxes has gone ahead and yes, homotopy in multi-way rewriting systems has unfold categories. I couldn't remember the name, but that's yes, that's exactly it. Okay, Ian. So there you go. Xerxes has that for you. Okay, well, we have about 2 minutes left, though I've been told that this will remain open. This chat will remain open for well, some time. So if you're interested in further information or just continuing the conversation, of course, feel free to continue to participate in this chat here. We can always extend the conversation to email, and well, it's I'm hesitant to share many details about this project because it's very much in its early stage, but I've shared what I think I can appropriately share within a half-hour period. And wow, this was fun. So thank you all for attending. Enjoy the rest of the conference and feel free to stay in touch. All right. Thank you for now. Goodbye.